everyone. My name is again Alexandra Mokrousova. Now I'm getting a master's degree in Novosibirsk State University, and today I want to speak about this topic: asymptotic relative efficiency of tests for checking correspondence to a regression model. I and my scientific advisor, Kovalevsky Artem Pavlovich, we have been studying this theme during the last year, and I believe this theme is really important because in plenty of scientific investigations we can see different regression models and two questions: how good our regression model corresponds to some data, and which way is better to check it. I think these two questions have a crucial meaning. And let's go to the introduction. A bit about the structure of my presentation. First of all, we define a regression model. Then we define hypotheses. After that, we speak about tests, and then we compare them in Pitman asymptotic relative efficiency mean. So let xi I eta I e I be the random vectors. I is equal from 1 to n, and it will be like this till the end of presentation. Variables xi I are independent and identically distributed with distribution function f. The second moment is exist and doesn't equal to 0. Components ei are independent and identically distributed too, with zero expectation and non-zero variance, which is equal to sigma n square. Also, ei are independent of xi I for all I, and the connection between xi I, eta I, and ei can be described by formula 1. Parameter theta is a known real valued and fixed. And about function j, I will say on the next frame, because C and K, I will say about this. We need next frame. Function j helps us to define hypotheses. The basic hypothesis h0 is j is equal to xi I, which means we have a simple linear regression model with one parameter. And each of following statements from 1 to 4 I considering as an alternative hypothesis HA. This is their formal view. I think it's a little hard to understand, but on pictures, first alternative, if we order in variables xi I and rename them and rename the result as xi, it will be look like this. This is the first alternative hypothesis. The function j is equal to xi I before some moment k, and then something went wrong and the function jump on some constant c. Where is c? Maybe it will be looks better. Second alternative says to us that we have a jump on constant c and change of slope of function. Third, we have a jump on some constant, function change a slope, but the correspondence is still continuous. And the fourth alternative, xi, and fourth alternative is about we don't have a linear regression model. We have a model which describes by power function, maybe like this. And about some details, c doesn't equal to 0 in first alternative and doesn't equal to 1 in others, because in this situation we just have a basic hypothesis. And k and c are unknown, real valued, and fixed parameters. K is such that because of this indicator function. Okay, let's go to the tests. Before we will speak about tests, I need to define some processes by which my tests will be constructed. Let xi, yi, and epsilon yi be a result of ordinary vectors xi I, eta I, ei by the first component. Then define theta with hat. It is an estimator of theta. Define regression residuals xi with hat, and their partial sums delta k with hat. And definition 1, process 1, empirical bridge is a random piecewise line z and 0 with hat of t built on these points, where sigma in square with hat is an estimator of sigma in square. Here I need to do some remark because when we say empirical, we assumed that all the components in this thing will be empirical. But here I use not the estimator of sigma in square, but only sigma in square, because sigma in square with hat tends to sigma in square almost surely when n tends to infinity. And further, if I speak about empirical bridge, I will speak about this line. And tests. Our test will reject a basic hypothesis if its statistic functional Jn takes the value on some critical set. And as functional Jn, we consider these two, Jn infinity and Jn int. I will call them supremum functional and integral functional. Okay, and now we can compare them. I will compare them in Pitman asymptotic relative efficiency sense, and it can be expressed as a ratio of Bahadur slopes. And this statement helps me to define the Bahadur slopes. First, if Jn divided by square of n tends to b of c in probability, when the alternative hypothesis holds, the distribution function of Jn converges to distribution function of J. It is a limit of Jn for all t as n tends to infinity. And finally, for some a bigger than 0, holds this, then the Bahadur slope can be calculated by formula 4.
Could you repeat who is Jn?
Jn, it's a statistic of tests. Okay, and to calculate the Pitman asymptotic relative efficiency, we just need to calculate coefficients a and b of c for each test. And let's do this. J, we have in statement 1, we have first condition, Jn divided by square of n, and to calculate coefficient b of c, it's really comfortable to define this process. In work, it got name wonderful process, and it is just empirical bridge divided by square of n. Then the last definition, I promise, general Lorentz curve. The theoretical general Lorentz curve is a curve defined by following formula. Lf0 of t is equal to integral from 0 to t f of f in power minus 1 of s by ds, and minus t times expectation of psi1. To calculate coefficient b of c, we need to find the limit of wonderful process. And I will speak about all theory, taking the first alternative as an example to don't take so many time. And let the first alternative holds. Then centered wonderful process converges almost surely to Q0 of t, where there is some mistake, where when t less or equal than t capital, whereas t capital is this. F, it is a distribution function of psi1. The process equals to this thing, and if t is bigger than t, then process limit of wonderful process equals to this thing. Looks big, but for uniform on 0,1 distribution distributed psi1, and when t is equal to 1/2, limit of wonderful process, it's just 2 parabolas. Okay, and now B of C, when the first alternative hypothesis is true, j and int divided by square of n tends to b int of C, and the same situation we have for supremum functional, and coefficient b int of C is equal to this thing, and if f is strictly monotone and continuous distribution function, then b infinity of C equals to this. If it doesn't true, and the distribution function f isn't continuous or isn't strictly monotone, then b infinity of C just equal to supremum of Q0 of t when t is from 0 to 1. Okay, lemma 3 is dedicated to calculation of coefficient A. For functional j and int holds this. This is a third condition from statement 1, as t tends to infinity, where a int is this. And fj int is distribution function of j int, and how you can see, it's just a distribution function of model of normal variable, random variable. And the main result of my work is theorem 1, Pitman asymptotic relative efficiency of test with statistics j and int and j and infinity for checking hypothesis h0 versus one of the 4 alternatives is equal to e int infinity, where all coefficients was defined in lemmas 2, 3, and the parameter a infinity is equal to maximum of this expression. And if e int infinity is bigger than 1, it means that for the first test we need more observations than to second one, and the second one is better than first one, and if it's less than 1, we have a completely different situation. And this is the main result of my work. I do this for all 4 alternatives, and I think this is the end. Thank you for your attention. Any questions? Yes.
Сейчас. То есть это не функция распределения нормального закона.
Модуля нормального закона. Да, да.
So, more questions?
Mm.
I have a question.
Okay.
In these cases, these can be applied.
I think in all cases when you need to use criteria like this, and in all cases when regression model is used.
And one question more.
Okay.
Can you return to your result?
Okay.
How do you check null hypothesis? You have 4 alternatives.
Oh, sorry. I think the it's can be mislead you. I have one basic hypothesis and one alternative, but as an alternative, I take different from this. These 4. I take one of them as an alternative.
Одна нулевая гипотеза и
Да, одна
произвольную.
Да, и берем произвольную альтернативу здесь. Да.
Okay, thank you.
То есть вы проверяете, можно ли это дело оптимировать линейной регрессией, правильно? Фактически.
По сути, да.
So, some more questions? If no, let's thank Speaker again.